Polarization of electromagnetic wave. See, this polarization is resultant of amplitude of electric field vector as a function of time at a fixed location, and observer is located along the direction of propagation. Or this polarization is orientation of electric field of electromagnetic wave. For example, if we have electric field vector of uniform plane wave, which is function of distance and time, and it is Ey0 cos omega t minus beta z ay. This can also be written as Ey ay, y component of electric field. This minus sign shows that uniform plane wave is propagating in plus z direction. Now I will draw this electric field as a function of z. This is x-axis, this one is y, and this one is plus z-axis. And these two dotted lines are the envelope of Ey. This point is plus Ey0 positive peak, and this one is minus Ey0 negative peak. And Ey is Ey0 cos omega, in fact Ey0 cos beta z. It will be like this, cosine wave propagating in plus z direction. Now if an observer is located along the z-axis somewhere here, then this will find that this waveform Ey is changing from plus Ey0 to minus Ey0 along the y-axis, up and down. So this observer will find that wave is coming towards the observer along this line, and its amplitude is changing up and down. So this wave is linearly polarized wave, or it is also called vertically polarized wave. If we have x component of electric field in place of y component, then this will be horizontally polarized wave, and the amplitude of observer will find that amplitude of this wave is changing from plus Ex0 to minus Ex0 along x-axis. So this is linear polarization, and it is also called horizontally polarized wave. Now what will happen if we have x and y components of electric field? Ez t is Ex0 cos omega t minus beta z. This one is x component, and Ey0 cos omega t minus beta z ay. Now we will draw the resultant in z0 plane, so better to write electric field as a function of time only. So this will be Ex0 cos omega t ax plus Ey0 cos omega t ay. Now let us assume that this is Ex0 cos omega t, and Ey0 cos omega t is Ey. If Ex0 is Ey0, means both the components will have same amplitude. In that case, we can see that Ex is same as Ey, or better to write Ey is Ex. Now if I keep Ex along x-axis and Ey along y-axis, then this equation is nothing but the equation of straight line passing through origin with slope 1. So resultant of Ex and Ey will be straight line passing through origin with slope, positive slope 1. At this point, Ex is maximum, that is Ex0. This will be Ey0. Similarly, at this point, Ex is minus Ex0 and Ey is minus Ey0, and this angle is tan inverse Ey0 by Ex0. If Ey0 is same as Ex0, then this angle is 45 degree. So the resultant amplitude will follow this straight line. So this is also an example of linear polarization, or sometimes it is called slant polarization. Now this can also be explained in this way. We have x component of electric field, which is function of omega t, and y component of electric field as a function of omega t. Both are having same amplitude. This is Ex0, and at this point it is Ex0, sorry, Ey minus Ex0. Now I will draw Ey. This is Ey0 cos omega t. Now I will draw the resultant of Ex and Ey in xy plane or z0 plane. This is resultant direction xy, and z axis is normally outwards. Positive z direction is normally outwards. In x axis we have Ex, in y axis Ey. Now when time is 0, when omega t is 0, Ex is Ex0 and Ey is Ey0. So resultant will be a point here. Now if I increase the time, for this particular time, say omega t1, Ex and Ey both are less than the peak value, and both the values are positive and equal. So resultant will be a point somewhere here. And when omega t is pi by 2, then Ex and Ey both will be 0. So resultant will be a point at the origin. Now if I go beyond pi by 2, or for omega t2, Ex0 is negative and Ey0 is also negative, and both the values are equal. So resulting point will be somewhere here. And for omega t pi, Ex is minus Ex0 and Ey is minus Ey0. So resultant point will be somewhere here. This is minus Ex0 and this point is minus Ey0. So if I joint all these points, then this will be a straight line passing through origin with slope unity, and the amplitude of resulting wave is changing along this line. So that's how we can explain the linear polarization. Now let us see what will happen if both the signals, x component and y component, will have different amplitudes. Ey0, suppose Ey0 is twice of Ex0. So E as a function of time is Ex0 cos omega t ax plus Ey0 cos omega t ay. This is Ex and this one is Ey. So Ey is Ey0 cos omega t. Now we know that Ey0 is twice of Ex0. So now Ey is twice of Ex. See, here we can see that both the components x and y component are having same phase but different amplitudes. Then Ey is twice of Ex. Now if I put Ex along x-axis and Ey along y-axis, then this equation is again equation of straight line passing through origin with slope 2. So this line will be something like this. It is tilted towards y-axis, or slope of line is now increased. This value is Ex0 and Ey0 is twice of Ex0. This value is minus Ey0, this value is minus Ex0, and this angle will be tan inverse Ey0 by Ex0, or it is tan inverse 2. Again, the resultant of amplitude of electric field will follow this straight line. So again, the wave is linearly polarized wave. Now let's see what will happen if x and y component are out of phase. For example, Ex0 cos omega t minus beta z with negative sign. This is x component, and y component is Ey0 cos omega t minus beta z ay. So let us make z0. So electric field as a function of time will be minus Ex0 cos omega t ax plus Ey0 cos omega t ay. This minus Ex0 cos omega t is Ex, and Ey0 cos omega t is Ey. Now if Ey0 is Ex0, then Ey is Ey0 cos omega t. This can be written as Ex0, because Ey0 is Ex0, Ex0 cos omega t. So Ey is minus Ex. Now this is also equation of straight line passing through origin, and its slope is minus 1. Again, if I draw Ey versus Ex, then this will be straight line passing through origin with slope, negative slope. So line will go like this. This point Ex minus Ex0, this is Ey0, and here Ex is positive and Ey is negative, and the slope of this line is minus 1. So the resultant amplitude will follow this straight line with negative slope. So again, this wave is linearly polarized wave. So now we can write the general expression for this linear polarization. If we have electric field which is function of z and time, and it has x and y components, ex0 cos omega t minus beta z, both propagating in plus z direction with phase phi x. X component has phase phi x and y component is ey0 cos omega t minus beta z plus phi y ay. Now if this phi x minus phi y is del phi and it is 0, pi, in fact plus minus pi, plus minus 2 pi, plus minus 3 pi and so on, or this del phi is plus minus n pi, where n is 0, 1, 2, 3 and so on, and whatever be the relation between the amplitudes of x component and y component, the wave will be linearly polarized wave. So this is linear polarization. Now let's come to the circular polarization. Circular polarization. First I am writing the general expression for electric field, that is Ex0 cos omega t minus beta z plus phi x plus y component Ey0 cos omega t minus beta z plus phi y ay. In case of circular polarization, Ex0 must be equal to Ey0. And let us assume that phi x is 90 degree or pi by 2 and phi y is 0. So now EZT is, or let's make Z0. Z is 0, so ET is Ex0 cos omega t plus 90 degree, this is x component, plus Ey0 cos omega t, phi y is 0. So electric field is, this will be Ex0 cos omega t plus 90 is minus sine omega t. Now let us assume that minus Ex0 sine omega t is Ex and Ey0 cos omega t is Ey. Ey is Ey0 cos omega t and Ex is minus Ex0 sine omega t. Now we have already assumed that Ex0 is Ey0, so Ex is minus Ey0 sine omega t. Now we know that sine omega t is the square root of 1 minus cos square omega t, and if I square both the sides, then this will be ey0 square 1 minus cos square omega t. So ex square is ey0 square minus ey0 square cos square omega t. Now this is ex square, that is equal to ey0 square minus, now this term is ey square. So this can be we can rewrite it like this: ex square plus ey square, that is equal to ey0 square. Now this ey0 is constant. So now if I put ex here and ey along y-axis, then this is equation of a circle. So the resultant of amplitude will be a circle. Here radius of circle is ey0. So this wave will be circularly polarized wave. Now we can also draw the resultant by drawing the x and y component with respect to time, and then we'll take the resultant. That will help us to find the direction of the circular polarization. Ex is minus ex0 sin omega t, and ey is ey0 cos omega t, where ex0 is same as ey0. Ex is minus ex0 sin omega t, so the curve is minus ex0 sin omega t. This is ex0, this value is minus ex0, and the second curve is ey0 cos omega t. So the second curve is ey0 cos omega t. Now we know that the resultant is a circle. We will just find out the orientation. Resultant of x and y component of electric field is a circle. Now let's find out the orientation. When phase is 0, when omega t is 0, then x component of electric field is 0 and y component of electric field is maximum. So this point is EY 0. Now if I increase the if I take omega t pi by 2, then x component is negative and maximum and y component is 0. So x component is negative and maximum and y component is 0. So the next point is minus Ex0. So for omega t, point was here, and for omega t 0, point was at Ey0, and for omega t pi by 2, the resultant is at minus Ex0. It means it is moving towards this direction. So we can say the orientation of this circularly polarized wave is counterclockwise or anti-clockwise, and the z direction is normally outwards. This is counterclockwise circular polarization. Now see, if this wave is forward moving, then the orientation of the resultant wave will satisfy the right hand, where curl of finger will show the orientation, and thumb will show the direction of propagation. This is the thumb is along the direction of propagation, and this curl of finger will satisfy the orientation of wave. So this is also called right hand circular polarization. Here phase difference between the two components is 90 degree. Phi x is 90 degree, phi y is 0, so del phi is 90 degree. If it is this del phi is pi by 2. If it is phi pi by 2, then also the resultant will be the same. For pi by 2, 5 pi by 2, 9 pi by 2 will have same resultant. Now let's see if phi x is 0 and phi y is 90 degree. Ex0 is Ey0, then Ezt is Ex0 cos omega t minus beta z. Phi x is 0. Ey0 is y component is Ey0 cos omega t minus beta z plus 90 degree. will make Z0. So ET is EX0 cos omega t AX, and this will be minus EY0 sin omega t AY. The resultant will be the circularly polarized wave. We will find out the orientation. So let's draw the X component of electric field. This is EX versus omega t. This is EX0 cos omega t. It goes like this. And Y component is EY is minus EY0 sin omega t. So this is minus EY0 sin omega t. Now we know that resultant is circularly polarized wave. We'll find out the orientation. When omega t is 0, then X component is positive and maximum, and Y component is 0. It means resultant is EX0. Now when omega t is pi by 2, then X component is 0 and Y component is negative and maximum. So resultant will be at minus EY0. So this circularly polarized wave is moving in this direction. Here omega t is 0 at this point. Omega t is pi by 2. So if I increase the time, then circularly polarized wave will move in clockwise direction. This is the Z direction. Wave is moving in plus Z direction. So this wave is, this is clockwise circular polarization, or it is also called, now see, if I put the thumb of left hand in the direction of propagation, then the curl of fingers of left hand will satisfy the orientation of this wave. The left hand thumb of left hand finger is along the direction of propagation. Then the curl of finger will satisfy the clockwise orientation. So this polarization is also called left hand circular polarization. Here phi x is 0 and phi y is, phi x is 0 and phi y is 90 degree. So del phi is phi x minus phi y. If it is minus 90, or better to write minus pi by 2 or minus 5 pi by 2 or minus 9 pi by 2, in all cases we will have same resultant. So now I can write the generalized expression for circular polarization. Electric field is E z t. It is Ex0 cos omega t minus beta z plus phi x ax plus Ey0 cos omega t minus beta z plus phi y ay. If Ex0 is same as Ey0 or both the components have same amplitude, and del phi, that is phi x minus phi y, is plus pi by 2 plus 5 pi by 2 plus 9 pi by 2 and so on, then it is counterclockwise or right hand circular polarization. If it is del phi is minus pi by 2 minus 5 pi by 2 minus 9 pi by 2, then this will be clockwise or left hand circular polarization, or del phi is plus 2n plus 1 by 2 pi, where n is 0, 1, 2 and so on, then it is counterclockwise or right hand circular polarization. And if del phi is minus 2n plus 1 by 2 pi, where n is 0, 1, 2 and so on, then it is clockwise or left hand circular polarization. Here we have assumed that wave is propagating in plus z direction because of this negative sign. Now if it means wave is propagating in plus z direction, or wave is forward moving. Now if wave is backward moving, or wave is propagating in negative z direction, in that case here still Ex0 is Ey0, and if del phi is plus 2n plus 1 by 2 pi, where n is 0, 1, 2 and so on, then it is still counterclockwise circular polarization. Now if wave is backward moving, then it will satisfy left hand, so the wave will be left hand circularly polarized wave. And if del phi is minus 2n plus 1 by 2 pi, where n is 0, 1, 2, 3 and so on, then wave is still clockwise circularly polarized, but if wave is backward moving, then it will satisfy right hand, so it will be right hand circularly polarized wave. Now elliptical polarization. Now I will start from the general expression for electric field Ex0 cos omega t minus beta z plus phi x plus Ey0 cos omega t minus beta z phi y. Here phi x minus phi y is del phi. If it is plus 2n plus 1 by 2 pi or minus 2n plus 1 by 2 pi, where n is 0, 1, 2 and so on, and Ex0 is not equal to Ey0, then the wave will be elliptically polarized wave. For this condition, if phase difference is 2n plus 1 by 2 pi, then this will be counterclockwise or right hand elliptically polarized wave. And if phase is minus 2n plus 1 by 2 pi, then the wave will be clockwise or left hand circularly polarized wave. Now it is very easy to explain if we know the information about circularly polarized wave. In circular polarization, Ex0 is Ey0. Now in elliptical polarization, Ex0 is not equal to Ey0. So let us assume that Ex0 is greater than Ey0. Now if I draw the resultant, Ex is along x-axis and Ey is along y-axis. If it is circular polarization, if Ex0 is same as Ey0, then the resultant will be a circle, something like this, because Ex0 is same as Ey0. I hope this is looking like a circle. Now if Ex0 is greater than Ey0, then the resultant will be something like this. Major axis is along x-axis and minor axis is along y-axis. This is the major axis, 2x0 major axis, and this one is the minor axis. Minor axis is along y-axis. Length of major axis is 2x0, length of minor axis is 2y0. And if Ey0 is greater than Ex0, then the resultant will be an ellipse, and the major axis of ellipse is along y-axis and minor axis is along x-axis. This point is Ey0, this is minus Ey0, this one is Ex0, and this one is minus Ex0. And for the orientation, we'll follow the same relation that we have followed in case of circular polarization. If phase difference is pi by 2, 5 pi by 2, then it is clock counterclockwise or right hand elliptically polarized. If phase difference is minus pi by 2, minus 5 pi by 2, then it is clockwise or left hand elliptically polarized, E. Okay. For forward moving, z direction is normally outwards. For forward moving wave, or wave is propagating in plus z direction. If wave is propagating in minus z direction, then counterclockwise and clockwise will remain same, but in place of right hand right hand elliptical polarization, this will be left hand, and for left hand this will be right hand elliptical polarization if wave is backward moving. Now let's write it like this: if wave is backward moving or propagating in negative z direction, and Ex0 is not equal to Ey0, and del phi is plus 2n plus 1 by 2 pi, then it is counterclockwise or left hand elliptically polarized wave. And if del phi is minus 2n plus 1 by 2 pi, where n is 0, 1, 2 and so on, then this will be clockwise or right hand elliptically polarized wave. Now we have one more condition in which the magnitudes of x and y component are equal. If Ex0 is Ey0 and del phi is not equal to plus minus n pi by 2, where n is 0, 1, 2 and so on. Or better to take it like this: if Ex0 is Ey0 and del phi is between 0 and pi by 2, then the resultant will be elliptically polarized wave, but major axis is not along x and y axis. The resultant is tilted ellipse. This will be the resultant, and orientation is counterclockwise. So this will be, if wave is forward moving, then this will be counterclockwise or right hand elliptically polarized wave. And if del phi is between pi by 2 to pi, then resultant will again tilted ellipse It's something like this, and its orientation is counterclockwise. Wave is forward moving or propagating in plus z direction. So this is CCW, counterclockwise or right hand elliptically polarized wave. Now if del phi is between minus pi by 2 to 0, then the resultant will be tilted ellipse or elliptically polarized wave. But the orientation is now clockwise. Wave is forward moving. This is clockwise or left hand elliptically polarized wave. And if del phi is between minus pi to minus pi by 2, then this will be the resultant tilted ellipse, which is rotating in clockwise direction. And wave is forward moving. So clockwise or left hand elliptically polarized wave. So that's how we can find out the polarization of electromagnetic wave.